Good morning, everybody. How are we doing today? In pain. Middle back. Like my neck is really happy now, but middle to lower back is starting to feel it. All right, we were talking directions and how to draw things in 3 dimensions while still drawing them in 2 dimensions and things like that. So what I want to do is point out a problem with this, and then we'll do a quiz to see how well you're doing with it. And then we'll move on and start applying it to wires and things like that. So I want to show you a video clip. And in the video clip, we're going to have a beam of electrons. And then there's going to be a magnet that comes in. And this is just an example of this force that we've been talking about, the Lorentz force, QV cross B. We're going to have a stream of electrons going across the screen. Why didn't that light go off? Ha-ha! I win. See if we can see that better. It's a little bit better. Okay. So this tube right here is going to have a beam of electrons going across, and they're going to indicate some directions for us.
We'll use this electron beam
to
demonstrate the deflection of electrons in a magnetic field.
So turn on the thing in the back doesn't matter. It doesn't matter. Okay, so here's the beam of electrons right here.
Beam running between
so we've got a velocity, don't we?
Glances along a phosphor screen.
And then
it shows the path
it's going
of the
more or less
electrons
straight
by the green
across
glow
the
where the electrons
tube
strike.
There. Bring your magnet in. It's phosphor, so you can see the beam of electrons. And then they bring in a magnet.
If we place a horseshoe magnet over the tube
and
with the north pole closest
it gets
to the
deflected
camera,
downwards, right? So which way is the force?
Downward.
Downwards, right? And then they flip the magnet.
If we reverse the magnet,
and pulls it upwards,
the beam
right?
is deflected
Which we'd expect,
upward.
right? So let's see if we can't kind of suss that out a little bit. So from that video, we had, what did they tell? I think the beam of electrons was going to the right, wasn't it? Yes. So the velocity was like that, okay? And then for the first one, the force was down, right? So this means that we can find the direction of the magnetic field, right? Okay? So let's take our right hands, everybody practice, right? So we know, where do we shake with our fingers? Or point our index finger? Direction of the velocity, right? And then in this case, we don't know the B, but we do know the F, right? And the F has to be down. So the magnetic field is pointing out. Wrong answer. No, not gaslighting you. What's wrong? We did the right hand rule correctly. No. What's wrong? What were the charges? They were electrons. Okay? So the magnetic field is actually pointed in. This is not my fault. This is Ben Franklin's fault. Okay, so the electrons are going this way, right? Okay. And I said the field is pointed in. My thumb is now pointed up. That's wrong, right? With negative charges, you must flip the answer when you're done. Do you remember how negative charges screwed us up with high and low potentials? And negative charges roll uphill and all that kind of stuff? This is the same thing, okay? Don't say it, Lewis. I don't want to hear it. There is a left-hand rule, but we don't use it in here. I don't use it in here because I'm forever confused about which hand is my right and my left anyway. And so I just get messed up if I introduce the left-hand rule. I've noticed in my teaching that when I've used left-handed rules, students end up doing worse on problems where they're indicating directions. I would encourage you to stick with the right hand, and what do you do if their charge is negative? You just flip the answer when you're done, whatever it is you're looking for. So let's do this again. Let's say I got my velocity like that. I've got magnetic field pointed in to the screen. So shake, field is pointed in the screen. My thumb is up, but because this is a negative charge, what am I going to do? Flip it 180 degrees when I'm done. So I do the normal right-hand rules for negative charges, everything, and then flip the answer. Okay? We knew that in the case of the video, we knew that the force was down, and we're looking for the magnetic field. So I go V, I put my thumb down for the force. My fingers are now pointing out of the screen. But the answer is, no, it's into the screen. Again, for a negative charge, find the thing you're looking for, and then flip it by 180 degrees, and you've got it. Okay? So just so you are aware of that. I better put down that this was an electron. Okay? Negative charge. So watch out. Watch out for those negative charges. They will get you. So let's do a quiz. Okay. So we did it for charges. What's a wire? It's just a bunch of charges all in a line, isn't it? Really? That's all it is. Doo-doo. So. Woo. All right, so the force on a wire, the magnetic force on a wire, F sub B, okay, turns out to be the current in the wire times the length of the wire crossed into the magnetic field. Okay, what do you know right away is going to be here? A right-hand rule, right? Because the cross product is sitting there. So we'll get to that in a second. Notice where the vector symbols have been placed. It's on length and magnetic field. Magnetic field makes sense. It's a field. It's a vector field, so it's going to have direction. But notice how we don't put the vector direction on the current. That's because current is not a vector. Current's a scalar, right? It's the amount of charge per second that's flowing down a wire or something like that. It's the actual length of the wire that is the vector thing, like there's the displacement that the current undergoes. In a practical sense, just look at the direction of the current. The direction of the L, the direction of the displacement of the current, is the same as the current. Okay? So when you're doing this, effectively, your right-hand rule is direction of current crossed into magnetic field, then you get the force, right? So I know we write it this way because we're being sticklers for what's a vector and what's not, but really in application, the right-hand rule goes between the direction of the current and the direction of the magnetic field. So I want to kind of talk about an issue here. And it's the fact that wires can really take on just about any shape in a magnetic field. So let's say I have a magnetic field that's pointed to the right, like kind of everywhere in this space. And then I have a wire that for some reason starts here, flows around like that, okay? And I'm just going to label these endpoints A and B right here, okay? And it's got a current that's flowing from A to B. We want to find the net force on this weirdo wire shape in this magnetic field. How are we going to do it? Not derivatives. Starts with an I, ends with integral. So we're going to have to integrate, aren't we? Yeah. And why are we going to have to integrate? Is there something that's changing here? It's like direction, isn't it? Because if we start near A, the direction of the length, the current flowing in the wire, right, is directly up, isn't it? And then we would rotate our hands in the direction of B. We'd have a force that goes in, right? But as this thing goes up and starts to curve, do things change? Does the direction of the force change? So over here, the current's in that middle section is almost moving to the right, isn't it? And I've got magnetic field to the right, but my thumb is still pointed in. And if I go back to up, so the direction here stays the same, doesn't it? What's changing then? The magnitude of the cross product, right? Because as this current goes from vertical, where the cross product would be the biggest, remember it's vector, vector, sine, angle between them. I've got almost 90 degrees here at the beginning. As I go towards the one that's almost parallel to the field, then that force is going to get much smaller. And then it gets bigger again. So we've got this force that's varying across this integral, right? So if I wanted to find the total net force, I'd have to divide my force up into little tiny segments and then integrate, right, over all those little tiny segments of charge. Well, that's pretty easy. I've got it right there in the box, right? It's going to be my current, which is staying constant, so I'll pull it out of my integral, times my dl, my little piece, right? I've broken this thing up into a bunch of little tiny pieces, right? Crossed into my magnetic field going from A to B. So I guess this is sort of a more general way of finding that force, right? You can do little tiny, you can do substitutions, right? You can say the dl cross B is dl times B times the sine of the angle between these two things, right? And then find a way to, parameterize this line in terms of theta, which just caused my brain to shut off. I don't know about yours, right? Like, I don't want to think about how I would make this an angle thingy. I'd have to know the function of the line and do all these weird kinds of stuff. Well, it turns out when you integrate this, the length that ends up mattering is the distance between the two endpoints. So we call this like an L prime, right? It's not the actual length of the wire, but it's the distance from where the wire starts to where the wire ends. There's an angle that could be found if I know where the wire is. Yeah?
Doesn't this have something to do with that mathematical concept about like it doesn't matter where the path from start and end point is the same?
Yeah, it's exactly the same thing. Okay, it's all the same mathematics as that idea that path integrals and directionality of integrals and things like that only depend really on the effective length of the path. Not the actual length, but just the distance from beginning to end. And so if I know the angle there in red, then I can literally just calculate it and do an end run around the integral, which is why sometimes you'll see this equation written as IL prime or like some other symbol on that L, which indicates it's not the true length of the wire. It's simply the effective length of the wire in the field, like the distance from endpoint to endpoint in the field. And I'll do an example of that, okay, here in just a minute. But well, I'll do it right now, actually. So what we're going to do, oh, no, we're going to watch a video instead. I forgot about the video. Silly me. Just to show you how much of an effect we're talking about, right? So we're talking about currents in a magnetic field, right? Check this out.
We'll use a large
so
horseshoe magnet.
She's got a really big horseshoe
current-carrying
magnet.
wire
She's got
to
a
show the
wire
force
connected to a
magnetic
switch.
field exerts
The switch is
on a
open,
current.
there's no current.
The
right?
wire is placed
But as soon
between
as she
the arms
applies
of the
a
horseshoe
current,
magnet.
go ahead and do it.
Then
do it.
12 amps is
I should
run
narrate.
through the
I go much
wire
faster.
in the direction shown by the arrow.
Freeze frame. Do you
The
see it
wire
jumping?
jumps out of the magnet.
Right? It jumps pretty far, doesn't it? This is a pretty big force that's acting on it, right? Jumps straight out of that thing.
This
Big
diagram
push.
shows the directions
okay?
of the current,
right-hand rule.
magnetic field,
Current,
and
magnetic
the force
field,
on the
yep.
wire as
Force is
predicted by the
out
right-hand
from
rule.
between the
If we
horseshoe
reverse the magnet
right?
and run the
they
same
turn
current
it
through the
around
wire,
and reverse
what
the
will the
direction of the
wire do?
magnetic field, what's going to happen? It's going to push down, isn't it? Because we go current, field that way. Now my thumb is pointing down. I really
This
don't need to
time
show
the
you the
wire
video here because
doesn't
it's not
leap
very
out.
exciting, but yeah, it just
the
stays in,
magnetic
right?
force on the current
Okay.
now
But
pushes
the
the
forces
wire
here
down.
are pretty big, okay? Just so you know. All right, so let's do a loop of wire. And we're going to do a shape that is going to look a little bit familiar to you. That's supposed to be a semicircle. Nope, it failed. I was hoping it would do a semicircle for me, but it won't. Okay, so there's my semicircle. So this loop of wire, so we've got current that's flowing that way, which means over here, right, it's going to flow around this way. So I've got a closed loop of wire, right, coming around. It has a radius r. And we're going to find the total force on this thing. Let's see, where's my magnetic field? I put my magnetic field pointing up. Now, I'm not going to draw that magnetic field everywhere because that would just make the diagram really messy, right? We just need to remember that no matter where we are, the magnetic field will always be pointed up, okay? So we're going to find the total force on this wire in this magnetic field. And the way we're going to do it is we're going to break up the two parts, okay, of this. We're going to integrate, but we're not really going to integrate. What I want to do is I want to do this bottom part separate from this part, right? Those two parts. So let's do the bottom part first, because that's more straightforward, right? So the magnetic field force on that current on the bottom is I L cross B, and I know my current. What's the length of that bottom wire? 2R, right? It's 2R. And then the magnetic field strength, and then sine of angle between them. See how I took away the cross product there by putting its magnitude in? All right, so sine theta, how do we deal with that? What's the angle between that current and the magnetic field? It's 90 degrees, isn't it? So what's the sine of 90? It's 1, isn't it? So this is 2RIB. And now we need a direction if it's going to be a vector. So this is where we're going to take our right-hand rule. Okay? So we're going to put our hand in the direction of the current and then bend our fingers upwards in the direction of the magnetic field, and my thumb ends up pointing which way? Out. And so I could say 2IRB out of page, or I could say plus K hat if I wanted to, because generally out of the page is your positive Z direction, right? Either of those indications are just fine and are used back and forth all the time in physics. Okay, so now we've got to do the top part. Okay, so we can integrate. I'm going to integrate just to show you that it's possible when you know the shape the function for the shape. But you should already know that we could use the effective length of the top part, right? But let's pretend I don't know what I'm doing. I'm just going to integrate. We go dl crossed into b. I think your book uses ds. Okay, so I've got to figure out what the parts of this integral are. Well, I know the current. That's easy. Okay. A to b. That's interesting. This is going to, so the cross product here becomes b sine theta dl. I kind of switched some things around in there, right? Because what's dl cross b equal to? Like magnitude-wise? I lost you. When you take a cross product between vectors, how do you find the magnitude? AB sine theta, right? So this would be dl times b times sine of theta. I just pulled the dl out. I rearranged the order of the terms there because integrals always have to end with the d something, don't they? What's the magnetic field doing over this integral? If I go, start here, and I go this way, which is the way I'm going to go because that's the way my current is going, right? What does B do? It's constant over that, isn't it? It doesn't change its value anywhere along there. So can I pull my B out? IB and sine theta d. All right. So now I've got to get this thing talking in thetas, don't I? How do I get dl, right? I'm going to cut up this arc into a bunch of little pieces, right? Yeah, it's the arc length, isn't it? Because arc length is equal to r theta. So this is going to be, r d theta. And I can just call this dl if I want to, because it's just a symbol. So there we go. I've got that. And then what are my limits? If I kind of make that switch. Yeah, it's 0 to pi. What happens to the r in this integral? It's constant. Ribs. Oh, 0 pi sine theta. Okay. So what's the integral of sine theta? Isn't it negative cosine? From 0 to pi. I don't know. I'm asking. I have no idea. It is negative cosine? Oh, goody. So let's see here. That's ribs minus cosine of pi minus 1 minus 1. Did I get that right? No. There's another negative. Negative, the negative positive 1. So what do I get? Right? I got a 2, basically, is what I got. But the negative sign was along for the ride for whatever reason. But the magnitude, since there's no direction here, this is just a magnitude, isn't it? 2IRB. So what direction, because I did this AB sine theta thing, what direction is the magnetic force? How do I find that? I found the magnitude. I've got to use the right-hand rule now, right? Okay. So the weird thing is I got to like change my direction while I'm using my right-hand rule, right? But over here on the right-hand side, I start with going up. Which way is the magnetic field? Up. What's the answer when I'm all the way there on the right-hand side? It's 0, right? But now it starts to curve, right? So now I'm getting a direction, and I got to rotate my hand to go up. Which way is my thumb pointed? In. If I'm at the top of the semicircle, I'm pointing to the left, up, still in. As I come around, coming down, it's still in, right? So the force magnitude changes, but that's okay. I calculated the magnitude with my integral, right? The direction is which way? It's 2IRB into the page, right? And so now what happens if I take the first part and I add on the second part? I get 0. I just discovered a really complicated way of writing 0. What's the effective length of this loop? 0. For any closed loop in a magnetic field, the net force is 0. I don't care what the shape is. Because for a closed loop, if it's a square, if it's a circle, if it's a triangle, if it's an elephant, I don't care what it is. If that current starts and comes back to exactly the same place, what will the net force be? 0. Why? Because the net effective length is 0. The distance between where it starts and where it stops, you'll come back, right? And your forces will all cancel each other out. This is fantastic news, isn't it? This is just great news because 0 is a handy thing to work with, right? The net force on a closed loop is 0. I'm done. I can go home. This is Mr. Balogh. This isn't hard. Guess what's not 0? The T word is back. What was torque? It's force, but worse. Right? It's the analog in rotation for force. It's the thing that causes angular accelerations, right? It's all these things. Okay? But let's talk about how the force on an object can be 0, but the torque would be non-zero. This is going to be important because what I'm about to explain to you is how every electric motor works. And why every generator works. It all begins right here. I'm going to draw, this is going to be hard. It's going to be hard, well, the math isn't that hard. But visualizing this can be difficult. This is supposed to be a rectangle that's got, it's not square, but the top and bottom are the same length and the size is the same. I'm just going to label these 1, 2, 3, 4, just so I can refer to the sides. This is just a teaching thing, right? This is just trying to keep everybody on the same page as to what I'm referencing. You don't have to label the sides of your doodad. I'm going to throw, let's see, we're going to get a current flowing around this thing all the way around. So this current is flowing, what is that, counterclockwise? Counterclockwise current around the loop. And we're going to have a magnetic field that points everywhere in the page to the right. All right. Let's find the force directions. We're not worried about magnitude for right now. Let's just find the directions of the force on each of the individual sides of my rectangular loop. And then we'll extend this to loops of any shape. So what is the force direction on side number 1? How do we tell? We put our hand in the direction of the current, which in this case would be to the left, and then we got to turn our hand so that we can bend our fingers in the direction of the magnetic field, only there's a problem. The direction is to the left, but then I've got to... What's the answer for the top and bottom? 0. what is the angle between the current and the magnetic field at the top? 180 degrees. What's the angle between the bottom and the magnetic field, where the current points to the right and the magnetic field points to the right? 0 degrees. And the thing that's common between sine of 180 and sine of 0 is that they are 0, right? So if you can't get a little bit of a bend in your fingers, then that means it's parallel. Just anytime a current and a magnetic field are parallel to each other, what's the answer? 0. Okay? Anytime there's a closed loop in a magnetic field, what's the answer? 0 for the net force. Yeah. Yeah. You can just say, it's closed loop, force is 0. See lecture. Right? Like, it's just, okay? So that leaves sides 2 and 4, doesn't it? Okay? So let's do side 2 here first, right? So what direction is the force on side 2? We put our hands, how do we face our hands first? Where do I put my fingers? Straight fingers go up. Magnetic field is pointed to the right, so I've got to do that. And my thumb is pointing which way? Into the page. So I'm going to label my force on this side. There's my force, right? And the X means what? Into, right? Okay, what about side 4? Which way do I hold my hand? I go down, and then to the right. My fingers bend to the right. Which way is my thumb pointing? How much is my shoulder hurting? All right, so it's not 0. The net force is 0. Yeah, but the forces on the individual segments are not 0. I mean, they're the same magnitude, aren't they? Pointed in opposite directions. Okay. But the torque here is not 0. Yes. Counterclockwise. CCW. All right. What I want to do, I want to mount this loop on an axis.
Can you demonstrate where the force is, like what it's doing for side 4 again?
Side 4, my current is down. My field is pointed to the right. There you go. Which way is your thumb pointed? Yep, there you go.
That's out of the page, wasn't it? Okay.
Did I get it backwards? Down to the, I did get it backwards. No, it's out. A dot is out. Getting my dyslexia all messed up. All right, so we got that right. Okay, so the green dotted line is an axis. Think of it like we could mount it on a rod or something like that. Okay, I'm just not going to kind of draw a rod in. And now I have to redraw this picture. What I would like to do is take this loop and take this flat plane and tilt it so that the bottom side 3 comes close to you, and we're going to look at it flat on. Does everybody catch what I'm talking about here? Okay. I want to take like the whole plane of the screen and I want to flatten it out like this. Okay. So I'm taking a page, right? Taking the page, we're looking at it like this right now, and I want to redraw the picture where we're looking at it like this. Does that make some sense? Okay. It's hard to talk about. It's even harder to animate, which is why I've never done it. Okay, so what would the loop look like if I tilted it so side 3 is towards us? It would just look like a line, right? That's what the loop would look like. And basically, this is like side 3 close to us, right? The axis that I defined is sort of pointing at us, right? So that means that the current on side number 2 is flowing into the page, isn't it? And the current on side 4 is flowing out of the page. How are we doing so far? This can be hard. This is why this is hard. You've got to take and think of it in 3 dimensions and sort of changing perspective on what we're doing. Okay? So what I've drawn there in the middle picture is a loop. It's just the flat plane of the loop, right? Where before we had, for current 2, we had current going up, right? And if I tilt the whole thing towards you, which way is my pencil pointed? In, right? Okay? So that's why I drew the X on that side. And then over here, the current is flowing down, right, in our flat page. And if I tilt it towards you, now which way is the current pointed? Coming out, right? Yeah, watch out. All right. Sometimes it helps to have pieces of paper. You can just fold them, and you end up with origami and right-hand rules, and then you end up in the nut house. So which way, and we'll do a right-hand rule, which way is the force pointed on segment 2? Notice, in rotating it, I have not changed the direction of the magnetic field. The magnetic field is still to the right, whether I'm talking about looking at it top up or like this. It's still, that didn't change the magnetic field direction at all. So if the magnetic field is to the right and the current is going into the screen, into right, which way is the thumb pointed? Pointed down. So my force is down. Okay, does that make sense? Yeah, before it was pointed into, never put this away, right? Before it was pointed into, no, it doesn't work. Okay, and then I rotated it. No. Good grief. I need thin hands. Okay, pointed into, and then I rotate it, and which way is it pointed? I'm going to stop trying. All right. So over here on the segment 4 side, which way is the current? Out. And then to the right, which way is my thumb pointed? Pointed up. Okay. Those 2 forces are equal and opposite, aren't they? They're the same magnitude, but they're opposite directions, which is why the force, the net force, is 0. But each of them acts at a distance r from the center of that loop. And does anybody remember what torque was?
Nope.
Yeah, r times F. Only the times is what? A cross product. How many cross products have we done so far? Right? Like, where did this come from? Okay, so torque is that. We could go and put this all together, but I'm not going to do the derivation. It doesn't take very long. But let's just say a miracle occurs. Okay? In the context of the current in this loop, we write the torque on this current loop as the current times A crossed into the magnetic field. I know it looks like A cross B, but it's not. That A right there is the area of the loop. But a vector. Lewis, is area a vector or scalar? It is a vector. Back in Gauss's law chapter, I showed you that area is a vector quantity, right? And many of you walked out changed as a person because you now had new knowledge, hidden knowledge, secret knowledge. This is a cult, isn't it? Like, we've got handshakes and hand signs and secret knowledge. No, it's not a secret. It's called physics. So,
This is a bad cult.
there's brainwashing and everything else. All right. So, What is A in this equation? Area. What is B in this equation? Magnetic field. This is not generic vector A times generic vector B. So what we've done in physics is we rewrite this as mu cross B. I know. It's mu vector. This is not friction. Okay? Mu is I times the area. And I know you're kind of like, oh, this is dumb, Mr. Balogh. Okay? I know. This mu right here, so this is how we write the torque, mu cross B. The mu, which is the current times the area, this is called the magnetic dipole moment. Not because it's having a moment, but because it's related to torque. We define the direction of this area. Remember how we had a little bit of ambiguity back in Gauss's law with like what direction the area could be? And I just kind of said, well, it's outwards, and I just left it at that. Well, actually, we have a right-hand rule for defining the direction of the area when it comes to these currents. What right-hand rule have we been doing so far? A handshake, right? You start with your hand, palm flat, fingers flat, thumb extended, right? And then you bend fingers or you do the gunshot, whatever, right? Okay. I call that the handshake set of rules. And it's exclusively used for finding forces on charges and currents. The second of the right-hand rules you're going to learn in Physics 4B, of which there's several variants, but the second classification is what I call the hitchhiker rule. Because when you're hitchhiking, what do? Well, you pull your phone out and call the Uber. Because what's Uber? You're getting murdered. Yeah, ask a stranger to come and pick you up and get in their car. But we pay for it now, so it's okay. Right? Don't hitchhike, Uber instead. Right? When you're hitchhiking, you tend to, in the old days before we had Uber, right? You would fold your fingers into your palm, right? That thumbs up. Maybe I shouldn't call it the hitchhiker rule anymore. Maybe I should call it the thumbs up rule. You've got your fingers curled into your palm, right? And your thumb is extended like that. What you're going to do is you're going to take your fingers. You're going to curl them or wrap them around in the direction that the current is flowing. It flows up the side of number 2, across the top of number 1, down 4, right? No matter which way I'm kind of thinking about it, my fingers will always flow around in this counterclockwise direction. Which way is my thumb pointing? Out. So that would be the direction of the magnetic dipole moment, and hence the direction of the area of that loop. Yeah, if it were flowing clockwise, it would be pointed in. Okay? On this sideways diagram, how do I wrap my fingers? What do I follow? I follow the direction of the current, don't I? Okay? So I'm coming into the screen over here on the right, wrapping around and coming out of the screen on the left. Which way is my thumb pointed? It's pointed up. So this magnetic dipole moment, I'll do it in red. This magnetic dipole moment, which is often drawn in the very center of the loop, would have been pointed up. There's a torque here because the magnetic field pointed to the right and the magnetic dipole moment pointed up. There's an angle here, isn't there? In this case, 90 degrees to start with, right? Will cause this torque to happen. And to find the direction of that torque, we're back to a cross product, right? Magnetic dipole moment crossed in the magnetic field. If we're doing that kind of thing, what right-hand rule do we use to do cross products? Handshake, right? What do you shake in the direction of first? Mu. In this case, it's mu cross B, right? So we go mu B, the torque would be directed into the screen. your brain needs time to sort this out. This is your first exposure. You're going to go wrestle with this a little bit and come back and be confused maybe tomorrow in GRASP or something, and we'll go through a bunch of different things. There were websites, I don't know if they're still active. There were websites that had like 60 like quiz questions on it. There was nothing but right-hand rule practice, right? So we need to go see if we can find some of those. We would just randomize them and give you the answers.
Is this similar to like the torque wheel we were talking about?
Yeah, same torque. It's just we're doing it with electricity now. Okay, so we can talk about energy here. This can get worse. We can talk about energy here, okay? I could, but I'm not going to. The potential energy of this loop is the dot product between the magnetic dipole moment and the magnetic field. So what the heck is going on here?
Was that a U?
That's a mu. It's the Greek letter mu.
No. That's mu. But is that mu too?
Oh, the big one is a U.
That's a U.
Yeah. How do you tell?
It was a little swivel.
There's no thing on the front, yeah. So if there's no thing on the front, it's a U. If it has an elephant's nose here on the front, then that's a mu. And why are mu and U so close to each other? History, the answer. Okay, so what's going on here? This is a dot product. So when is the potential energy like the greatest? What must be the angle between these two things in order to have a big number? No. Because the dot product goes vector, vector, cosine theta. And 0. Right? Okay? So when mu and b are lined up, you have the greatest potential energy. But more importantly, what's going to happen if we sort of let the loop go? It's going to feel this torque, and what's it going to do? It's going to rotate, isn't it? In fact, this one is going to rotate this way. Why? Because forces are being applied.
Oh yeah, you're right.
Yeah, just look at the forces.
Because how far they are from the center.
Yeah, right? Because there's distance from the center, all that kind of stuff. This loop's going to rotate, isn't it?
You have to put like a 0 somewhere.
What's a rotating metal loop? It's a motor. Only this motor isn't going to work. Why is this motor not going to work? Well, it starts, right, with magnetic field this way, and the loop and the magnetic dipole moment that way. But now it's going to rotate, right? And the magnetic dipole moment's going to go like that. And what happens is the magnetic dipole moment gets closer and closer to the magnetic field vector direction. It goes to 0, doesn't it? But this loop probably has mass because it's made out of something, right? Which means it's probably going to rotate. It's like going to have some inertia. But now that we're on this side, the directions flip. Huh? Okay, so I got to draw this better. The loop starts. Let me only draw the magnetic dipole moment of the loop, okay? So that's the magnetic dipole moment. Which way is the loop oriented? Always perpendicular to this, right? Okay, so the loop begins to rotate, which means the magnetic dipole moment will eventually get to this orientation, won't it? And then sometime later, it's going to be going in this orientation as it begins to spin around, right? But the problem is, I have mu and I have b, and I've got b, and I've got b. Do your right-hand rule on the first one. Mu crossed into b, which way is your thumb pointed? In, right? Now we do this one. Mu, b, which way is your thumb pointed now? Out. The torque reverses direction when it passes that 0 point. And so, what is this loop going to do? It's going to start, it's going to go past, and it's going to get pulled back, and then it's going to go past, and maybe there's some losses or some friction. If there wasn't any friction, it was a perfect system, it would just flip back and forth, which isn't very useful. We need this thing to go around, don't we? That's the whole idea of a motor, is it continues around in the same direction. How do you do that? Change either the field direction, or the easier thing to do, change the current direction. Every what? Every pi rotation, every 180 degrees of rotation. We're getting ahead of ourselves, but I wanted to give you a taste of where we're going, right? These are the very basic physics of an electric motor. Where are electric motors nowadays? Everywhere is the answer.
Even in your phone.
Yes. Okay? A motor in my phone? Yes.
Why don't we be making that noise?
The haptic engines, the buzzes that you feel. Oh, that Instagram came. Where does that oscillation come from? If you want, you can think about it as magic. Motors are everywhere. They're in your microwaves, they're in your coffee makers, they're in your refrigerators, they're making their ways into cars. It's how we generate our electricity. Like, they're everywhere. Okay? Without the electric motor, we wouldn't have society the way we have it now. Maybe we wouldn't have Facebook. That'd be a good thing. Who was the person that first invented an electric motor?
Was it Tesla? It was that one girl.
Was his last name Motor? Abraham Lincoln. Just kidding.
Oh, Benjamin Franklin. Phelps.
Michael Phelps.
He was old, isn't it?
Michael Faraday. Who I've already mentioned, right? He's coming back around. And you'll see why. You'll see why. Okay.
Enchilada? Is an enchilada motor? I'm ready for a mic drop.
All right, let's put it all together. And what do I mean by putting it all together? Magnetic fields aren't the only things in town. What did we spend the first 9 weeks of this class looking at? Electric fields. Okay. All right. The total net force acting on a charge is the force from its interaction with an electric field plus the force from its interaction with a magnetic field. QE, we got all the way back in the second chapter of this course, and it kind of stuck with us the whole time, didn't it? I mean, even in circuits, we were still kind of, the electric field was pushing stuff around and doing all these things, right? Okay. A lot of times, this is called, or it's written as Q and then E plus V cross B, right? Just to pull the charge out. But I like this form written out here because it gives a distinction between the electric force and the magnetic force, right? The charge is experiencing forces from electric fields and forces from electric fields. And you might say, well, Mr. Balogh, why would you do both, right? Like, what's the whole point, okay, in doing both of those things? And my answer is cyclotrons. My answer is mass spectrometers. No. And all of the chemists in the room just went, huh? Electric fields and magnetic fields together. Here's some pictures of cyclotrons. The closest cyclotron to you in your everyday life is probably your local hospital. Not an MRI. not a CT scanner. Those of you that have unfortunately have had to have radioactive tracers injected into your body before you undergo, say, an MRI or a scan of any kind, okay? Where do they get those radioactive things from? The basement. Okay? Sometimes, not so much in basements anymore. Sometimes there's a company here in town that will be producing the radioactive tracers. The thing about those tracers is that they have half-lives that are really, really short. They're measured in minutes. And so you have to produce the medications like on site. You can't produce them, say, in a place we don't care about like Nevada and have it shipped, okay, to here, right? Because in the shipping time, the radiation, it would decay so much that it would be useless as a medical diagnostic. So different companies specialize in this. Several major hospitals just have a cyclotron in the basement. A cyclotron takes a charge, and through a nifty combination of things I'm about to explain to you, will whip that charge around in a circle, get it going close to the speed of light, and have that charge bombard a nucleus, hopefully knocking some of the things out of the nucleus that will make it unstable. And then you can put that unstable thing into somebody and get a picture of what their insides look like without having to cut them open and let all the demons out. So the cyclotron you see in the picture, you see the ruler for scale, right? That's more of a kind for making radioactive isotopes in hospitals. They get bigger. That's a picture of a bunch of old white guys, right, at UC Berkeley, standing next to one of the big cyclotrons that they use. They've torn them down now, but when I went there in the 90s and early 2000s to do research, some of the old cyclotrons were still there in their buildings, and you could walk around them. They were kind of museum pieces. But Lawrence, of Lawrence Livermore fame, he built these big cyclotrons, and they used them to make a lot of elements that were not found in nature. So, like plutonium, all kinds of things. So anyway, what's going on in a cyclotron? You got some magnetic fields. You have a place where the charges can move, and then it's called two Ds. They literally just call them Ds with a cavity in between. The path that a charge will take in a magnetic field. So let's say, let's do magnetic field pointed into the page. And then we're going to send a positive charge. We're going to send it into the field moving to the right initially. Okay? So as this charge enters the field, it's going to experience a force. Do you agree or disagree? I'll say anything to get an A, Mr. Balogh. Yes. Okay? So we're going to experience a force. What force are we going to experience? The magnetic one, right? We don't have any electric fields here yet. Okay? So what direction will the magnetic force be on this particle? It's going to be up. We put our hand, shake to the right. Magnetic field is coming into the page. My thumb is pointed up, right? Up, correct. So the force will be up. Well, if the force is up, what is that going to do to the velocity vector? It's going to shift, right? It's going to change it. And so the velocity vector is going to start moving that way, isn't it? Well, now what direction is the force? Well, it's always perpendicular, right? Mutually perpendicular. So now it's going kind of like that. So which way is the force now? Kind of like that. And now it's going like this. What is this called? Yeah. When you have a force that's pointing towards the center of something, that is called a centripetal force, and centripetal forces make things go in circles, don't they? So, charges shot into magnetic fields will circulate. They'll circulate around the magnetic field lines. We can take advantage of that circulation in a cyclotron with these D-shaped magnetic fields. So if we get some magnetic fields in our Ds like this, right? And then we put an electric field in the gap between the Ds. Now our particle is going to curve around, and then here, as soon as it gets out of the D, it's not going to be curving anymore, right? But now, what is it going to do with the electric field? Accelerate and speed up, right? And then curve, and then get accelerated again. And so what starts as a small curve gets bigger and bigger and bigger as this thing gets more and more speed. And finally, it gets whipped out one side, and we can take advantage of that really, really fast. So cyclotrons can get things up to like 99.99% the speed of light, no problem. Okay, that's a small, I was about to say household version. It's a small like hospital type version, okay? The biggest cyclotrons in the world, you've heard of the Large Hadron Collider in Geneva, Switzerland, okay? That's got a circumference of like 40 miles or something. Like it goes underneath the Alps and comes back out, right? Like it's buried underground, right? Just huge, and that's a cyclotron of sorts. It doesn't have big Ds in it. Instead, it's got just one long beam path that they use pulsed magnets in to get it to speed up the charges that are in there. They can get those up to 0.9999999% the speed of light. What's that? They use magnetic fields, but they don't use Ds. They're just trying to contain the plasma. We'll get to that later. The CERN is the organization that operates the Large Hadron Collider. There's other colliders at CERN, but CERN's like the laboratory name. It's the European Center for Nuclear Research, but it's the French acronym. Yeah, they have different experiments all happening on the Large Hadron Collider, but they also had other colliders and other research that's going on there. All right. So that's one application, right, of magnetic fields and charges. I talked about mass spectrometers, right? I mentioned them a little bit. We have some here in this building in the chemistry department, okay? What does a mass spectrometer do? Spectrometers. A spectrometer is a device that breaks things up into its constituent parts for measurement, right? So you can have light spectrometers, mass spectrometers, all these different. But a mass spectrometer means that we're breaking up something into its mass components. What the heck does that mean? Okay. Well, here is a mass spectrometer output for glucose. What's glucose? Sugar. What color is sugar? White. And you put it into a little baggie. And now you have a white powder in a baggie, right? So when the very nice police officer is asking you about your white powder, right? You could show him or her the mass spectrum for your white powder. Because this spectrum is unique to glucose. These are the fingerprints of molecules, okay? We're going to talk about how the mass spectrometer works here in a second. It's very different from, say, other white powders.
Oh, this is where cocaine comes in.
This is where cocaine comes in, okay?
Oh, is that how they catch you?
What's that?
Do they catch you?
Is that how they catch you?
Well, like, just
Louis, do we need to talk? Yes, this is how you determine what things are, right? What is the chemical substance that you have? Why would you want to know what a chemical substance is? May I? What's in this bottle? Are you sure?
No.
How could you tell?
It's not clear.
Oh, if you get a bag, you don't know what it is.
knowing what's in our water supply becomes very, very important, right? Mass spectrometry is a way. There's other ways. There's better ways, actually, to figure out what's in water. But a mass spectrometer is a device, right, that can fingerprint and give a unique signature for different molecules, different chemistry, right? So how does it do it? Well, it's a box. You put stuff in, magic happens. No. This is how it works. I'm going to get the first part today. I might not get to the second part today. Mass spectrometer consists of two parts, a velocity selector and then the detector. By the way, this is not how you go and build a mass spectrometer. The engineering is actually very difficult. Okay? This is the theoretical mass spectrometer, simplified. It starts with something called a velocity selector. And in this velocity selector, what do you think a velocity selector does? It selects a velocity, right? Okay, I know, it's amazing, isn't it? Let's say that we've got a positively charged plate up here and a negatively charged plate down here. What exists between the plates? What field? An electric field, right? I'm just going to draw one of the vectors, but there's many, right? Okay, I just want to be clear here. And then, okay, so if a charge comes into this region, which way is it going to go? It's going to go down, isn't it? It's going to follow the electric field. And if it's a negative charge, it'll come in and it'll go up and it'll slam into that plate, right? But the electric field alone is not enough to get the velocity we want. What we want, is for the charges to go through in a straight line. But we also want to know what the velocity is. So what we need to do is we need to balance the force on this charge with a magnetic force going up. So if our charge is moving to the right and we want, oops, that's not the magnetic field, that's the force. We want the force magnetic to be up. We know the force electric is down. What direction does the magnetic field need to be pointed in order for this to happen? Well, I know my force is up. I know my velocity is to the right, right? So V to the right, thumb up. Which way does the magnetic field have to point? In. So I know I have a magnetic field, oops, in red, pointed in, right? So now I have a situation where the electric force and the magnetic force have to be equal in magnitude if I'm going to get a nice straight line here. If the electric force is stronger, what will the charge do? It'll go down. If the magnetic force is stronger, what will the charge do? It'll go up. What's the only way for this charge to go through straight? For those to be equal. And in order for those to be equal, I need QE to be equal to QVB. Where'd QE come from? The whole enchilada, right? The force on a charge in an electric field. Where'd QVB come from? The other part of the enchilada, right? And why did I not do the cross product? I'm just looking at magnitudes, right? I fixed the directions already, right? I just need the magnitudes. And why is the sign not there? What's the angle between that magnetic field and that velocity? Not 180. 90. Sine of 90 is 1. What cancels out? Does it matter if the stuff going in is singly, doubly, or triply ionized? Nope. Which leaves me with an interesting relationship, right? The velocity that any charge is going to have will be equal to the strength of the electric field divided by the strength of the magnetic field. Who knew that a Newton per meter divided by a Tesla was a meter per second? It is. But that velocity will be the velocity of a charge, a molecule maybe that's lost some of its electrons, okay? as it passes through the velocity selector. Now, in a mass spectrometer, you can't pick. You put in your sample, it gets blown to smithereens, and you cannot pick you can't really pick what the charges are or the speeds of these things. They're just generated at whatever speed they get. And so you'll have stuff that will slam into the top, stuff that will slam into the bottom, but the only stuff that makes it through is what? The stuff that's moving at a speed that you know. On Tuesday, we're going to take that speed and we're going to use it to find out what the atomic mass of that charge actually is. Monday's lab, you have oh, you don't have the lab packets. That's because they're right here, and I forgot to hand them out. So, take a lab packet on your way out. Sorry, Damon, you're going to get tackled. Okay? Make sure to grab a lab packet on your way out. And I will see you, if not tomorrow, I'll see you Monday. We are doing the Intro to Magnetic Fields lab. I put the circuits lab in there because I forgot to print it. We'll do that later. Oh, yeah. Oh, yeah.